Okay, let's try and see how far we can get through all of our examples, different examples of circular motion. So we're going to start off really easy, go on to some harder ones. Number 1, 2,000 kilogram car makes a lap around a flat circular track in 15.7 seconds at a constant speed. The curve has a radius of 50 meters. So I'm just labeling everything we know. We seem like we know the mass, the time, the radius right off the bat. What is the circumference of the track? So just again, to make sure that we know what we're talking about, here's our circular track. Here's our radius of 50 meters. The car is moving around that. So circumference, this is a middle school problem, circumference equation is equal to 2 pi r. So our circumference is equal to 2 times pi times 50 meters. If we multiply that all together, we do not get 100 pi meters, although that is technically an answer. I don't want you writing things in terms of pi, because off the top of your head, you don't know what 100 pi is equal to. You couldn't tell me how many meters that is exactly. What I need you to do is multiply that out, okay? And again, that's just, I guess maybe 100 pi you could figure out, but if I said like 8 pi meters, you wouldn't really have an understanding of how big that is. So 2 times 50 is 100, times pi is about 314 meters. And that's our circumference. That's how far the car travels to go around once. What is the speed of this car? Well, it says it's moving at a constant speed, so therefore we can use average speed equals distance over time. The distance that's being traveled is the circumference. Circumference in this case is 314 meters. The time is 15.7 seconds. So the average velocity or speed here, shouldn't say velocity, is 20 meters per second. And again, that's constant because it says that it's moving at a constant speed. What's the centripetal acceleration? We know that AC equals v squared over r. So we just found the speed, that's 20 meters per second, over a radius of 50 meters. 20 squared divided by 50. We get a centripetal acceleration of 8 meters per second squared. What direction does that point in? Points in towards the center of the circle. What direction is this average speed, or is this speed in right now? Right now, it's like this. Let's just say it's moving counterclockwise. That usually makes sense. So up and to the left, but that will change as we go around the circle. The acceleration will always point in towards the center. So the vector, how it's oriented, will change, but it will always point in towards the center for AC. What's the magnitude of the centripetal force? Fc equals MAC. M is 2,000 kilograms. AC is 8 meters per second squared. Fc equals 16,000 newtons. And again, what direction does that point in? That always points in towards the center of the circle. A little bit trickier, what force or forces provide the centripetal force? So remember, centripetal force is not a new force all by itself. It is simply a force, excuse me, it is simply the net force in the direction towards the center of the circle. Other forces act as a centripetal force. So imagine that we were trying to draw a little picture of what the car looks like here. Imagine you're behind the car. Okay, there's your rear windshield, and the car is turning at this point. If you're behind the car is going around this way, it looks like the car is turning to your left. I realize this is, let's pretend this is flat. There we go. We have a net force, or excuse me, a normal force pointing up from the road surface. We have a force of gravity pointing down. And what force allows that car to turn? If there was no friction, that car would not turn. It would simply go straight through the turn. Okay? So friction, from the perspective here, so this is the behind view. The friction must point in like this. So our free body diagram, I don't really count this as a free body diagram. Our free body diagram looks like this. Fn up, Fg down, and Ff toward the middle. Oh, we've forgotten our axis. Our axis, remember, for circular motion, we have C pointing in towards the center, and we have Fn and Fg that are not pointing in towards the center or aligned with the center at all, so we're going to have the positive Y direction there. What provides the centripetal force? We just got done saying Fn and Fg are not in the direction towards the center of the circle, only Ff is. So only Ff, the force of friction, provides the centripetal force. Written another way, we could say that the centripetal force is equal to Ff. Now here's a good question. If we assume that the centripetal force provided is the largest force of friction possible between the tires and the road, that's key. What's the coefficient of friction between the tires and the road? So what's going on here is that phrase largest force of friction possible is supposed to trigger something in your mind. It should remind you of something called the maximum force of static friction. Even though the car is moving, this is actually an example of static friction and not kinetic friction, because kinetic friction has to do with something sliding over a surface. And if you think about how tires work, tires don't slide over a surface. Tires, like only a very small portion of the tire is in contact with the road at any one point, and then it gets picked up and put down again, and picked up and put down again. That point on the tire is never sliding with respect to the road surface. So this is actually static friction. So I'm just going to write that in here. Max force of static friction. Okay, so we're talking about the maximum force of static friction here. And you should remember that the maximum force of static friction we can determine by using this equation, Ff equals mu Fn, which is good because we just determined that the force of friction is the centripetal force in this case. So we already know the centripetal force. We're looking for the coefficient. We don't know the normal force, but because we have that free body diagram already drawn, it's very easy to find that. F net y equals Fn minus Fg equals may. This car is not accelerating up off the road surface or down into the road surface, so ay must be 0, making that entire thing 0. Fn equals, and I'm just going to change this to mg. So the normal force is 2,000 kilograms times g, we're going to use the AP version of 10 meters per second squared. Fn is 20,000 newtons. So I come over here and I plug in 16,000 newtons for the force of friction equals mu times 20,000 newtons. Mu is 0.80. Pretty high mu, but yeah, you're going around a fairly tight turn. Well, I guess not super tight, but you're moving pretty fast around that turn. You need a pretty high coefficient of friction so that you don't slide off. And as a matter of fact, what happens if either the car goes faster or the curve was tighter? Well, let's think about it like this. If the curve is tighter, then the radius is smaller. If the car goes faster, then obviously the speed is faster. If v increases or r decreases, that's going to increase the centripetal acceleration. And if you increase the centripetal acceleration, you're going to, assuming the mass stays the same, which it would, you're going to increase, in case you want proof of that last calculation, you're going to increase the centripetal force, which means you need a bigger force of friction. But we just said that that force of friction is as big as it can possibly be. So if you go either faster or the curve is tighter, then you're not going to be able to negotiate this curve. The car would slip to the outside of the turn and not negotiate the curve as wanted. Another way of thinking about it is the car would end up going too straight. It's not that you would go perfectly straight, you're just going to be making a bigger turn than you otherwise could. Your tires would slip, you would spin, you would kind of end up moving to the outside. The car would go too straight. You might ask, well, you're trying to do, in one of those cases, you're trying to make a smaller radius. How could you go more straight? You know, if you're trying to turn harder, how would you end up going more straight? It's that your tires would end up skidding, okay, and you would end up moving to the outside of the curve. Okay, so the first 4 or 5-ish of those are pretty easy Regents level questions. This last one is on the border between Regents and AP. Let's move to some other questions. This next one is a real interesting one. Okay, good, I'm centered here. What is the centripetal acceleration given to us by Earth's rotation? Very strange, kind of vague question, but let's try something. We know centripetal acceleration is given by AC equals v squared over r. So if we can figure out the speed and we can figure out the radius of an object that's on Earth as Earth rotates, we can figure out the centripetal acceleration. Well, the radius shouldn't be too hard to do. This is on your last year's Regents reference tables. It's not given to you on the reference tables for AP this year, but in any case, at any time that you need it, it will be supplied to you. The radius of the Earth 6.37 times 10 to the 6th meters. So that's important. Earth's radius, r equals 6.37 times 10 to the 6th meters. Now, how do we figure out Earth's speed? And this is gonna be a little tricky, but we can do it. We know. Let's start, somewhere kind of simple. We know that Earth makes 1 revolution per day, so I'm just going to write that as 1 rev per day. Now we probably want that speed in meters per second. Okay, how can we figure out how fast 1 revolution per day is in meters per second? Well, let's do some unit conversion. We know we can convert days into seconds. We're going to take a couple steps to get there. I'm probably going to convert 1 day to 24 hours, and then I'm going to say 1 hour is 3,600 seconds. But that's a pretty simple conversion into seconds, okay? And if you are confused about 1 hour being 3,600 seconds, remember there's 60 seconds per minute, 60 minutes per hour, that's 3,600. Now what about that revolution? Think about what happens as the Earth rotates. A point on the Earth goes through 1 revolution in a day. And 1 revolution just means that point makes 1 complete circle. It's like it's tracing the perimeter of the Earth. Okay, so it's making a giant circle. If we can figure out the circumference, if it's tracing the perimeter of a circle is the circumference, if we can figure out that circumference, then we could convert how big 1 revolution is into meters. And as a matter of fact, we can do that because we know that 1 revolution, since it's equal to 1 circumference of Earth, would be 2 times pi times the radius of Earth, 6.37 times 10 to the 6th meters. And if we multiply all this together, we should get the speed of Earth's rotation. So we take 1 revolution per day, divide by 24, divide by 3,600, and multiply by 2 times pi times 6.37 e to the 6th. And what we get is 463.2 meters per second. Now, I'm going to put a star on this. Okay? This is the rotational speed at the equator. Think about at the North Pole. Okay? If you imagine a point on the equator as it undergoes 1 full revolution as Earth spins, it is moving 463.2 meters per second. It travels through a huge distance. Imagine a point on the North Pole, or very close to the North Pole. The circle that point traces out is not going to be very big. Matter of fact, it's going to be very, very small because it's not, that part of the Earth does not have, the points there do not have a very high linear speed. They don't have to rotate that much. They have to rotate 360 degrees, but they're so close to the North Pole where a point wouldn't move at all as the Earth rotates that their distance that they move through is very, very small. So the speed actually increases as you go down towards the equator, okay? So at the equator, this is the linear speed of a point on Earth, and this varies based on latitude. Okay, so we can now plug in and solve for the centripetal acceleration. We have 463.3 meters per second squared divided by 6.37 times 10 to the 6 meters. So I'm going to square this, and I'm going to divide by 6.37 e to the 6th. And what I end up with is a very, very small centripetal acceleration of 0.03 meters per second squared. This is the centripetal acceleration that an object would have if it was on the equator, okay, and moving in a circle because Earth rotates in a circle. Now, think about what direction that centripetal acceleration would be in. It would point towards the center of Earth. Do you know of any other accelerations that point towards the center of the Earth? Acceleration due to gravity. So this centripetal acceleration, and by the way, what is causing the centripetal acceleration? What is causing the object to move in a circle with the Earth? The force of gravity. So this is very interesting. And it turns out that a very small effect, of the acceleration of falling objects is due to Earth's spin. So in other words, what this means is that at locations that have high, we'll call them linear speeds, like near the equator, the Earth, the force of gravity from the Earth on that object, doesn't just accelerate it straight down, it also has to allow that object to move with the Earth, to kind of accelerate it around with the Earth. So what this does is it actually reduces how much the acceleration due to truly just plain, straight down due to gravity is at that location. The Earth actually bulges out at its equator and is flattened a little bit at the poles because of this. Objects near the equator aren't pulled straight down as much due to gravity because we have to account for their spinning around of the spinning around that gravity does. So the Earth actually bulges out at that point because its own gravity is not pulling itself in as much. It's a little bit of a complex topic. I have to work through it every time I see it, so I encourage you to go and look a little bit more about this up. It's a very interesting idea, but it does really happen. It is proved. Okay, so we see that there is an object at the equator does have a centripetal acceleration. It's very small, but that actually takes away from the acceleration due to gravity at that location. Okay, so objects would not accelerate at as great a rate straight down as they would in other places. If you try this at the poles, where there is no centripetal acceleration because the object is just turning in place, it's not moving around at all, you would find a slightly greater acceleration due to gravity because the Earth doesn't have to pull that object around with it, cause it to rotate with it. All right, enough about that. Really quickly, let's do number 3. A man swings a ball on a string in a vertical circle. Ball has a mass of 0.5 kilograms and the string has a length of 0.9 meters. So here's a picture. We want to draw free body diagrams for when the ball is at the top, sides, and bottom of the circle and write net force equations in all situations. So here's what we've got. Okay, here's the ball 0.9 meters away at the top, side, and bottom. When the ball is at the top, we have our ball. The positive the direction towards the center of the circle C would be down at this point, and there's two forces pointing down, both the tension pulling the ball down and the force of gravity. Okay, so the net force equation in this case would be the centripetal force, the net force in the direction towards the center of the circle, equals tension plus Fg. When it's at the middle, or at the side I should say, we have this free body diagram. We have tension pointing to the left, force of gravity pointing straight down. Our net force, or our axis, let's see, towards the center of the circle is to the right, so that's going to be C, but we also have this Fg, so I'm going to put in a Y direction as well. Okay, our net force equations now are going to be F net Y equals negative Fg, because it's in the negative Y direction, and Fc is simply T. When it's at the bottom, the positive direction, or the direction towards the center of the circle is up, so that's plus C. And we have tension pointing up, force of gravity pointing down, and now we have Fc equals tension in the positive direction minus Fg. Okay? So now we're going to take a look at the top and bottom of this circle. At the top of the circle, the magnitude of the string's tension is the same as the weight of the ball. So what does that mean? That tells us that T equals Fg here. Determine the ball's speed at this point. So let's look at the net force equation at the top. We already had Fc equals T plus Fg. If T is equal to Fg, then we can just replace this with Fc equals Fg plus Fg. And as always, we do have to end a net force equation with ma, in this case mac, since we're talking about circular motion. So not only is this 2Fg, I'm going to go a step further, and since Fg is equal to mg, I'm going to write 2mg equals m times v squared over r. So I'm going to combine that all in one fraction. I'm going to cancel out the m's here. Notice that I have m on this side, m on this side. If I divide both sides by m, they cancel out. I'm trying to solve for v, so I'm going to multiply the r to the other side. So I get v squared equals 2gr. Take the square root of both sides. I see that the velocity is going to be given to me by the square root of 2 times g times r. 2 times 10 meters per second squared times the radius is 0.9 meters. 2 times 10 times 0.9, 18. Take the square root, 4.24. So that's the speed of the ball at the top of this circle. If, in fact, the ball was at that point, it would be moving that fast. And the tension was equal to the weight of the ball. Now at the bottom of the circle, the magnitude of the string's tension is the same as the weight of 7 similar balls. So this time we have tension equals 7 times the weight of the ball. Notice we never actually had to know the mass for that question. I wonder if that'll be the same here. Determine the ball's speed at this point. Same sort of process. Write the net force equation. Fc equals T minus Fg equals MAC. The tension is equal to 7 Fg. So that would be 7 Fg minus Fg equals MAC. 6 Fg. Oh, I'm just going to simplify that into 6 m little g equals mv squared over r. Now it's pretty much the same process as before. V squared equals 6 gr, square root of both sides. V equals 6, g is 10 meters per second squared, r is 0.9 meters. Now, we get 7.35 meters per second. So we see, is this uniform circular motion? No, it is not. We know it's not uniform circular motion because the speed changed from the top to the bottom. And when we get into energy, we'll see why that speed had to change. Okay? So there's some basic problem solving with circular motion. You'll find the problems are fairly similar to these. Hopefully they're a little bit easier now, and I'll see you for our last circular motion topic in a little bit.